Imagine you are looking at a star that has died and left behind a glowing corpse. Now imagine that around this corpse there is a ring of dust and rocks that are the remnants of planets that once orbited the star. What would you see? What would you learn? How would you feel? This is not a science fiction scenario, but a reality that we can observe with the most powerful telescope ever built, the James Webb Space Telescope. Today, we will talk about one of the most amazing discoveries made by James Webb, the observation of a white dwarf star and its debris disk. A white dwarf is the remnant of a star that has exhausted its nuclear fuel and shed its outer layers. A debris disk is a ring of dust and rocks that orbit around a star. Some white dwarfs have debris disks that are thought to be the result of collisions between planets, asteroids, or comets that once orbited the star. In this video, we will explain how James Webb was able to observe the white dwarf named WD-0145+234 and its debris disk in infrared light. We will also explain how this disk was formed by the fragmentation of large bodies that had liquid water on them, which is similar to how some bodies in our solar system, such as Earth and Mars, have carbonates on their surface. Finally, we will discuss what we can learn from this observation about the evolution and fate of planetary systems around white dwarfs. So, let's get started. The newly observed white dwarf WD-0145+234 is located about 170 light-years away from Earth in the constellation Pisces and has a mass of about 60% of our Sun, but a radius about 100 times smaller. This means that it is very dense and hot, with a surface temperature of about 15,000 degrees Celsius. Around this white dwarf, there is a debris disk that extends from about 10 to 60 times the distance between Earth and the Sun. This disk is very faint and hard to detect because it reflects very little visible light from the white dwarf. However, it emits infrared light that can be detected by James Webb. So Webb used its near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, to observe this white dwarf and its debris disk in different wavelengths of infrared light. By analyzing the spectrum of this light, James Webb was able to measure the temperature, composition, and distribution of the dust grains in the disk. The observation revealed that the disk has two distinct regions: an inner warm region with a temperature of about 900 degrees Celsius and an outer cold region with a temperature of about -150 degrees Celsius. The observation also revealed that the disk contains silicate and carbonate grains, which are minerals that form in water-rich environments. This observation was published in a scientific paper by researchers from NASA, ESA, and other institutions. So how did this debris disk around this white dwarf form? And what does it tell us about the history of this star system? The most likely scenario is that the disk was formed by the fragmentation of large bodies that had liquid water on them. These bodies could have been planets, asteroids, or comets that once orbited this white dwarf when it was still a normal star like our Sun. As it aged and ran out of nuclear fuel, it expanded into a red giant and engulfed some of its inner planets. Then it ejected its outer layers into space and became a white dwarf. The remaining planets moved into new orbits due to gravitational interactions with the star and each other. Some of these planets may have collided with each other or with smaller bodies, creating a cloud of debris around the white dwarf. The debris gradually settled into a disk due to gravity and collisions, and the inner part of the disk was heated by the radiation from the white dwarf, while the outer part remained cold. The presence of silicate and carbonate grains in the disk suggests that these bodies had liquid water on them before they were destroyed. Silicates are common minerals found in rocks such as sandstone and granite. Carbonates are minerals that form when carbon dioxide dissolves in water and reacts with rocks such as limestone and marble. They are also found on the surface of Earth and Mars, where they indicate the presence of past or present water. The detection of carbonates in the disk around the white dwarf is very rare and surprising because carbonates are easily destroyed by high temperatures and ultraviolet radiation. This means that the disk must have been formed recently, within the last few million years, and that the carbonates must have been protected from the harsh environment by a layer of dust or ice. One of the most intriguing questions in astrobiology is whether life can exist on planets around white dwarfs, as they are very stable and long-lived sources of light and heat, which could make them suitable for hosting habitable zones. However, they are also very dim and small, which means that their habitable zones are very narrow and close to them. This poses several challenges for planets in these zones, such as tidal locking, atmospheric loss, and irradiation. The observation of this white dwarf and its debris disk suggests that some planets around white dwarfs may have had liquid water on them before they were destroyed. This raises the possibility that these planets may have also had life on them at some point in their history. However, it is unclear whether life could survive or thrive on these planets after they were disrupted by collisions or by the star's evolution. Our own solar system will eventually face a similar fate as WD 0145 plus 234's system. In about 5 billion years, our sun will become a red giant and swallow Mercury, Venus, and possibly Earth. Then it will shed its outer layers and become a white dwarf. The remaining planets will move into new orbits, and some of them may collide with each other or with asteroids or comets. A debris disk may form around our sun's corpse, containing traces of our former home. This observation can help us understand how planets form, evolve, and interact with their host stars. It can also help us explore the possibility of life on other worlds and the potential for habitability around white dwarfs. Planets form from disks of gas and dust around young stars. These disks are similar to the debris disks around white dwarfs, but much larger and more massive. By studying the debris disks, we can learn about the composition, structure, and dynamics of the original disks that gave birth to planets. Planets also evolve over time due to various factors, such as tectonics, volcanism, erosion, climate change, and impacts. These factors can alter the surface and atmosphere of planets and affect their potential for life. By studying the debris disks, we can learn about the history and diversity of planets that once orbited white dwarfs and how they changed over time. Moreover, planets interact with their host stars throughout their lifetime. These interactions can be beneficial or detrimental for planets, depending on the type and stage of the star. For example, young stars can provide energy and warmth for planets, but also bombard them with radiation and stellar winds. Old stars can destroy or perturb planets as they expand or contract. So by studying the debris disks, we can learn about the fate of planets that survived or perished around white dwarfs and how they influenced or were influenced by their stars. This observation is not only fascinating but also important for our knowledge of astrophysics and astrobiology. It shows us how powerful James Webb is as a tool for exploring the universe in unprecedented detail and depth. It also shows us how diverse and dynamic the universe is, with stars dying and planets colliding. It also shows us how precious and fragile life is in this cosmic drama. We hope you enjoyed this video and learned something new from it. If you did, please give it a thumbs up and share it with your friends. If you have any questions or comments, please leave them below. And don't forget to subscribe to our channel for more videos like this one. Thank you for watching.